This is the 8th video in the series of lectures on linear algebra. So in this video, I'll take up the topic row space and column space of a matrix. So consider a matrix A equal to 1, 0, 0 and 0, 1, 0. So actually, these are the two vectors in RQ. One is 1, 0, 0 and another is 0, 1, 0. I am writing those vectors in the row as the rows of a matrix, and this is the matrix formed by that. It has 2 rows and 3 columns. It is a matrix of side 2 by 3. Now, row space of a matrix is nothing but span of the rows of a matrix. So this is the first row and this is the second row. You know that any rows of a matrix or any columns of a matrix are nothing but vectors in their particular spaces. Like if you have a m by n matrix, rows of a matrix form vectors in m r to the power 3, and here in this case columns of this matrix forms vectors in R square. So if you have a m by n matrix, rows of a matrix are vectors in R to the power n and columns of a matrix are vectors in R to the power m. So if the field is R, this will apply for any general field F also. So spanning set of R1 and R2 means linear combination of the rows of the matrix. So it gives you alpha, beta, 0, such that alpha comma beta belongs to R. So which is a subspace of, subset of R cube. This is nothing but xy plane. Alpha, beta, 0 is nothing but xy plane. It's a kind of projection. Okay. Now, if you want to, this is the row space. If this is the row space of the given matrix, or else it is the space spanned by the vectors 1, 0, 0 and 0, 1, 0. So row space is nothing but it is the space spanned by the vectors or space spanned by the rows of the matrix. Now if you want to get dimension of row space of A, then that is also called as a rank of A. Row, it is the symbol rank of A. That is called as dimension of row space of A. So now to get the dimension of a row space of the given matrix, what you should do is the matrix has to be reduced to the row echelon form or row reduced echelon form to find out its rank. How many linearly independent rows you have, that you have to count. If you get the non-zero rows, you have to count how many non-zero rows you have. Then that gives you the number of linearly independent vectors. Number of linearly independent vectors gives you the dimension of the row space, or it is also called as rank of that matrix. So now here it is already in the row echelon form, especially row reduced echelon form. So therefore basis, the given rows form the basis, that is 1, 0, 0 and 0, 1, 0, because it is a subspace of Rn. Every time row space of a matrix, m by n matrix, is a subspace of R to the power n. If you want the column space of the matrix, it is the span of the columns of the given matrix. That is alpha 1 0 plus beta into 0 1, linear combination of alpha gamma into 0 0. So this is nothing but alpha beta. Okay, such that alpha beta belongs to R. So it is a subspace of R square, especially it is nothing but equal to R square, entire R square. But in this case, this is not entire R cube, it is subspace of R cube. You know that xy plane is subspace of the given space R cube. But in this case, this is also a subspace, but it is entirely equal to the given plane R square. So dimension of the column space is also 2, because these columns are also, though there are 3 columns, you have to check any 0 column is any vectors, any set of vectors having 0 vector is not linearly independent. So you have to exclude that 0 vector. So linearly independent columns you have to count. There are 2 linearly independent columns, or for a column space you have to count the columns which have the pivot. The first column has the pivot, second column has the pivot, third column doesn't have any pivot. Therefore, these 2 columns are linearly independent. So count those pivot columns, that gives you the dimension of column space of A, that is nothing but rank of the matrix. And the basis for this column space of A is nothing but those linearly independent columns 1, 0 and 0, 1. So from these two, what you can conclude is dimension of row space of A is equal to dimension of column space of A, the given matrix. This conclusion we can do from these 2 results. Column space need not be equal to row space, because here the column space is a subspace of R square, here the column space is subspace of R cube, so no question of equality there. But dimension, number of elements in a basis of row space of the given matrix and column space of the given matrix is always equal, and that a particular value is called as rank of the matrix. So if you have reduced the given matrix into the row echelon form while finding the row space of the given matrix with the help of row space of the given matrix, in that case you have to count non-zero rows to get the rank of a matrix. If you are using it with the help of column space, so in that case you have to count the number of columns which have pivot to get the dimension of the column space. So if you count number of columns in the row echelon form, that may not give you the proper answer. You have to count number of columns with the pivots, that gives you the rank of the matrix, if you are making use of the concept of column space of the matrix. So let us take one example, how to find dimension of row space of the given matrix or rank of a given matrix. So consider the matrix. It is a 2 by 3 matrix. Now reduce this matrix to echelon form or row reduced echelon form. Anything is fine. But for finding the rank, you may require that row reduced echelon form, or you can just use echelon form also. What I am going to do is I am making this is the first non-zero entry of the first row. Any entry, first non-zero entry of the second row should be to the right. So I have to make it that happen now. Change R2 to in such a way that 1 minus 1, that becomes 0. 3 minus 0, 3. 4 minus 2, minus of my here, this R2 plus R1 I have to do. 1 minus 1, 0. 3 plus 0, 3. 4 plus 2, 6. So this is in row echelon form. So you can conclude here itself that it is number of non-zero rows is equal to 2. Hence dimension of row space of A is equal to 2. Okay, rank of A equal to 2. Suppose if you want to still convert it into the reduced row echelon form, you can do that. First non-zero entry should be equal to 1. So multiply the first row by minus 1, 1, 0, minus 2, second row as it is. Now you have to make the second row's first non-zero entry also equal to 1. So divide the second row by 3. 1, 0, minus 2, 0, 1, 2. Elements above the pivot and below the pivot, you have to make them 0. Already they are 0. So now this is in the row reduced echelon form. So why this form is needed? Because if you want to find the basis, you know that dimension of the row space of A is 2. So the basis for the row space of A should contain 2 vectors. Which are those 2 vectors? These 2 linearly independent rows will form the those vectors of the basis. So 1, 0, minus 2. This one, minus 1, 0, 2, 0, 3, 6. This is one basis, okay, which is in the row echelon form. If you have the row reduced echelon form, that is minus 1, 0, 2, 0, 3, 6. 0, 3, 6, that is also a basis. And 1, 0, minus 2 and 0, 1, 2, that is also a basis. There are different possibilities. And first row and second row both are linearly independent because here you have in the row echelon form you have non-zero rows. So the given vectors corresponding rows also form a basis. That is this. Okay. The vectors which are in echelon form form basis. The vectors which are in non-zero vectors, non-zero rows which are in row reduced echelon form a basis. And here R1 and R2 in the row echelon form are linearly independent. So corresponding rows of the given matrix also form a basis. So here see, actual row space of A is nothing but span of the rows of the matrix. So when you span these, you will get alpha minus 102 plus beta into this one. So this row space will be in this form. There are 3 coordinates doesn't mean that it should be exactly equal to R cube. So it is a subspace of R cube because dimension of the row space of the given matrix is not equal to 3. It is equal to 2. It is a smaller space than the R cube. Now, basis means any vector can be written as a linear combination of those vectors. Now x alpha into 1, suppose if I take this as a basis. Now 1, 2, 2 belongs to row space. Okay, you can check. Can you write 1, 2, 2 in terms of all these basis vectors? Yes, minus 1 first basis. And we can write 1, 2, 2 with respect to second basis. That is also 2. 1, 2, 2 with respect to the third basis. So all these form basis for the row space of the given matrix. Now if you want the column space, if you want to find the column space of the given matrix is span of C1, C2, C3, that is equal to span of these columns of the matrix. Okay. So that is nothing but you will get two coordinates. It's a subspace of R square. It is a 2 by 3 matrix. So column space is always a subspace of R square. Row space is always a subspace of R cube. So now dimension of column space, reduce it to row echelon form or reduced row echelon form. Anything is fine. Now when the last result, you should not count the non-zero columns. Here you have to count the columns which have the pivot. First column has a pivot, second column has a pivot, third column doesn't have it. This is not a pivot, this is some entry. This is the first non-zero entry of any column is called as pivot. There are two columns with the pivots, hence dimension of column space becomes 2. Because we know the result dimension of column space is always equal to dimension of row space. So if that should satisfy, you can't count it as 3. We are not counting non-zero columns. We are counting the number of columns which have pivot. But if it is row space, we are counting number of non-zero rows. So now these all acts as a basis. First column and second columns are linearly independent. This shows that they are linearly independent. So these vectors minus 1, 1, 0, 3. The corresponding columns of the given matrix forms a basis because they are linearly independent, and this can also be a basis, that is minus 1, 0, 0, 3, and this can also be a basis because it is one more form of reduced row echelon form, and this is the total reduced row echelon form 1, 0, 0, 1. That can also act as a basis. So if you have a m by n matrix, column space is also always a subspace of Rm, and row space is always a subspace of Rm. So this is all about row space and column space of a given matrix. So in the next video, I will take a few problems that will help you to understand the row space and column space of a matrix in a better way. Thank you for watching.